what I'm going to talk about tonight is water quality testing. There's basically two types, freshwater and marine. And in society, we forget about the freshwater testing. Go right on to marine testing. Basically, there are two types of kits, inexpensive and expensive. One of the things you need to look at, though, when you're looking at cost, you need to look at cost per kit and cost per test. A lot of people look at kits and are sometimes turned off by the high price of the kit, but very often it's a much better bargain than a lower price kit, which does a lot fewer tests. So that's always look at how many tests a given kit does. Don't just look at the price. If you buy a kit that does only 20 tests, you're going to use it up pretty quickly. In kits, you've got basically different approaches to reagents. You've got dry reagents, liquid reagents, and that's basically it. Your dry reagents take on different forms, and there are advantages and disadvantages to all of those. With dry reagents, generally you're talking about tablets, like aquarium farms, dry tabs, for example. Or you're talking, the other version are the powder pillows, which are basically made by hand and are used by a number of manufacturers. Aquarium System uses them, Morin uses them, and several other test kit manufacturers use them. Dry reagents have a reputation, or are believed to be more stable than liquid reagents. And sometimes that's the case, and sometimes it's not. One of the disadvantages to dry reagents, particularly tablets, is that they are usually not more stable because they are compressed under pressure. To form a tablet, that brings the components into very intimate contact. And if there's any moisture at all in there, they're much more likely to react than if they're in a solution. The other drawback is they're very hard to dissolve. It takes quite a bit of time sometimes to get those tablets dissolved. For some tests, they don't make any sense at all. If you're trying to measure a gas, like if you're trying to measure oxygen or CO2, and you're using a tablet that you've got to shake the hell out of to get it dissolved, you're not going to have a reliable result. So they're not a very good approach for that. The disadvantage to the pillow is that it's sometimes very hard to get all the reagent out of the pillow. So that if the amount of reagent is critical, it's very important to get all that powder out of the pillow. If you can't get it all out of there, you may not have reliable results. Liquid reagents, on the other hand, have a reputation of being not as stable, and in some cases that is true. I'll give you some examples in a little while. The main advantage to liquid reagents is that the concentration of the reagent is fixed, and it's generally more reliable to get a constant amount of reagent added to whatever you're going to measure by adding drops. If you've got a good drop dispensing unit, generally your drops are fairly consistent in size and how much reagents they will deliver. So that's one of the big advantages of liquid reagents. Plus, liquid reagents are generally a lot easier to use. It's a lot easier to drop something into a solution than to try to shake a tablet or add powders to it and shake that up. So that's one of the things you need to consider. Other factor that's involved in looking at testing are the colors and the color scale, the type of color that the kit produces. And bear in mind that probably most of you don't have a spectrophotometer sitting at home to look at these colors. So you're going to have to look at them with your eye. And the human eye is notorious for not judging colors very well, not judging intensities of colors very well, finding it very difficult to compare one color to another reliably. Your wife may say, well, it's this, and you'll say, my wife thinks it's that. We can argue about it. But that's just typical. So whenever you're looking at a test kit that is not going to be read by an instrument, but is going to be read by the human eye, you have to take into consideration those factors that affect how the human eye sees color. I've got here some examples of different types of kits that you're probably familiar with. Tetra, this is the aquarium system. Cordon has something very similar. Seachem, which is a little different from all the others. What you're looking at in these is you're looking at transparent colors. Basically, you look through a container, hold it up to the light or against a white background, and you're looking through it and you're comparing it to a reference. In this case, what you're doing is you're comparing a transparent color against an opaque color scale. That's not very reliable. You're going to have a lot of trouble making reliable comparisons. In this case, it's not that critical because really what you're looking at is you're looking at no ammonia, a little amount of ammonia, a moderate amount of ammonia, a lot of ammonia. You don't really, even though they give a number, that's really all you're concerned about. So it really doesn't make that much difference. But if you were really concerned about getting a number, you would have a lot of problems doing that reliably because the color that you're going to get through here is a transparent color. You're comparing it to an opaque color, something that is not transparent. This is a little better because you're looking at a transparent color and you're looking at a color scale that is transparent. I don't know how well you can see that out there, but most of you are probably familiar with this. There's one little problem with it, which is typical of these things. If you look at yours, this one, you can't see it from there, but the color, even within the same squares, within the square is different. Around the edge, you've got a darker color, and around the middle, you have a lighter color. It's true of all of them, so it's kind of hard to tell, well, which color am I supposed to be comparing to? And that's a characteristic of doing this type of thing, where what they're doing really is they're starting out with something that's all the same color and overlaying different. You're just overlaying more of the same, you're just building up the color that way. And what it does is creates aberrations around the material so that it gets to be difficult to compare colors. It works. I mean, there's really nothing wrong with it, but you have to be careful when you're looking at it. The Seachem approach is a little different in that we use test wells. What this does, one of the big differences between these and the test well is that what you're really looking at is a reflective, what is almost a reflective color. You're really looking at an opaque color. The color generated is against a white background. You're not looking through very much sample. And the test relies on the generation of basically an opaque color or a reflective color. So you're looking at something reflectively, and you're comparing it against a reflective scale, basically an opaque scale. So you're looking at the same type of thing. For those of you who use our kits probably don't recognize this because our new color scale is a continuous scale. And for those of you who say I can't tell one color from the other, what we're doing is we're doing this type of thing where you slide back and forth. This happens to be a business card. We won't just fun with this. Right now this is basically what we're going to do. Just slide this back and forth together. And you compare it to what you get in the scale. So that is another approach to comparing colors. None of these are perfect. They all have their limitations because you're dealing with the human eye. For some people, one approach might be better than the other, depending on how you see colors. At Seachem, we think that this approach is a very good approach because you're doing reflective color against a reflective scale. The other reason we like this is you can do more than one sample at a time. That basically is what you're looking at when you're looking at kits. These are the choices and the types of approaches. Generally, these are very economical. These are your inexpensive kits. And there's nothing wrong with it if it does the job. I mean, there's no need to spend more money than you need to. If this is satisfied with what this does, you don't need to spend 3 times what this costs to get something that's a little bit more sophisticated. Sounds like I'm pushing Tetra. Yeah.
I noticed on the color gradients that we've got all shades of blue or all shades of green, but I've seen some test kits that actually have go from shades of dark blue to a green or blues to reds.
Right.
Which are very, very different. Clear cut.
That's a very important point. Another thing to consider when you're looking at test kits, depends on the test. Some tests you can, and some tests you can't. You've got 2 things that the human eye can look at. One is a hue difference, and the other is an intensity difference. And in some cases, a combination of both. For example, this scale has both. It goes from yellow to green. Theoretically, if you push this far enough, you could go all the way to blue. But basically, you're going from yellow to green, and as the color changes, the intensity increases as well. In this here, what you're doing is you've got 1 hue. So all you're looking at here is an intensity change. You have no hue difference. This is harder for the human eye to judge because you've only got 1 piece of information that's being fed to your brain, and that's the intensity difference. Whereas this, you've got 2 pieces of information being fed to your brain. Likewise, you have 2 pieces of information being fed to your brain. It depends on the test. This happens to be a phosphate test, and the chemistry that they're using in this phosphate test, basically what you're doing, you're generating 1 color, period. The way we do a phosphate test, what you do is you're generating, really what you're generating is you start out with you're still generating a blue color, but you're starting out with a yellow, you're generating a blue and a yellow, which gives you a blue. And that's a very important point. If you can get a kit that has a hue difference as well as an intensity difference, that's generally better than one that only has an intensity difference. Looking at specific tests, pH is a very important one. And there you'll run into different types of situations. Generally, a lot of the pH tests use there are 2 common indicators that are used. One is thymol blue, which generates a yellow, green, blue color, and the other one is wrong trestle purple, I don't remember what it is. Anyway, that one generates purple color. That's aquarium system uses that particular dye, and that I don't know why they favor that, because all that dye does is goes from light purple to dark purple. It's very difficult to judge where you're at. Thymol blue, at least you go from a yellow, green. You barely get to the blue because the blue is never going to be that high, but at least you go through yellow and green. At Seachem, we have a proprietary dye that we use, which goes from pink at 7.6 and to blue at 8.4. So we go from a pink color to a greenish blue to a blue. It's a narrow range dye, which helps to give you a more accurate pH because you actually become a true blue almost right around 8.3. If you don't have a true blue, you're below 8.3. If you've got something darker, you're above. But generally, you're 8.3. After a while, you don't even need the color scale. You just look at the sky blue, it's 8.3. And it's a proprietary dye, which I'm not using it. Ammonia is another important test. In that test, there are 3 basic chemistries out there for measuring ammonia. One is a very cheap and economical one. This is one where I advise everybody to stay away from it because one, it's unreliable, and 2, it's too toxic, and that's Nestle created. That test gives you a yellow color to ammonia. It gives you a yellow color to lots of things. So it's basically unreliable. The other thing that's bad about it is that it's a mercury compound. It's a fairly toxic mercury compound. I keep expecting it's being pulled off the market, but it's still there. I don't advise using it. You can't use it with most. You chlorinators, most ammonia removers will follow it up. Just about a lot of things you use in the aquarium will follow it up. Nestle's reagent was originally designed to measure ammonia that was distilled from a sample into a clean container of distilled water. So basically we were distilling ammonia out, passing it through a gas phase into an aqueous phase, and then measuring it in that phase. It was never intended or designed to work with an organic soup that a reef tank or a marine tank or any kind of aquarium. It was never designed for that. The other approach is the salicylate test, which most companies use, aquarium systems use it, Cordon uses it. And that's the test that gives you a green to blue color with ammonia. It's also referred to as the phenol hypochlorite reaction. Basically what it's using a phenol and a hypochlorite bleach to form a blue dye. Sometimes they use salicylate, which is basically aspirin, which is a phenol, to develop the reaction. And generally it takes about 5 minutes to develop the reaction. It's generally pretty reliable. They don't all behave the same way. If you get Tetra's salicylate test and aquarium systems of salicylate test, you'll find that with a lot of samples, you'll get different types of reactions because they're not formulated exactly the same way. Generally, Tetra's tests are cheaper than aquarium systems. Seachem uses, again, a proprietary technology for ammonia. We use a sensor technology where you might be familiar with it in our ammonia alert. We just leave the ammonia alert on the water and it registers ammonia on a continuous basis. We do the same thing in our ammonia test kit. We use basically the same sensor where you measure free ammonia. If you want to measure total ammonia, you just add something that raises the pH up to 12. That's all ammonia free, and then you measure the total ammonia that way. The sensor technology is based on the fact that ammonia is a gas. And the way it works is it has a reagent in a hydrophobic membrane. The membrane does not ever get wet. Put it in the water, but it doesn't get wet. Totally repels the water. It will never wet. No matter how long you leave it in the water, it will never wet. Ammonia is a gas. The free ammonia as a gas basically crosses that membrane. And there it changes the color of the reagent that's embedded in the membrane. If the ammonia goes down, the ammonia that's in the membrane will leave the membrane, and the color of the membrane will go back. So basically that's how that works. The advantage to it, obviously we think it's the best thing out there, but the advantage to it is that it's not susceptible to any chemical interference with whatever you have in the water. If you're using ammonia remover or any chemical that's in there, it can't get to the sensor unless it happens to be a gas. One of the things that can get to it is your fingers. You put your finger on it, that will damage it because you have oil in your fingers. So if you use anything that is not anything that can get across a hydrophobic membrane, like oil in your skin or soap or detergent, something like that, that will get inside the membrane and that will damage it. But other than that, there's really nothing that will damage the membrane. These membranes will last for years. Another important common test is nitrite and nitrate. And I put those together because basically they're measured the same way. What you're doing basically is measuring nitrite, regardless of what you're doing. What is actually being measured is nitrite. Were you after? Nitrite is reacted with a dye to form a diazomic reaction, which gives you a red, generally a red or orange, depending on what is used, and that measures nitrite. And just about everybody uses the same, basically the same reaction. Some people use different chemicals, they give you slightly different colors, but it's all basically the same reaction. Nitrate is measured, when you measure nitrate, you use the same reagent, except you treat the sample with a reducing agent that converts the nitrate to nitrite. So basically what you're doing is taking that nitrate and reacting it, converting it to nitrite, and you measure that. Basically what you're doing is really measuring a nitrite that's formed from the nitrate. everybody uses the same reaction here as well. Reagents for measuring any of these are basically the stability of those reagents, whether they're liquid or dry. Really doesn't matter. They all have pretty much the same. There's really no advantage to using dry or liquid in any of these. Another common test that's important for the reef people, but nobody else really in the green tank is phosphate. And this is a phosphate kit, the C-test kit that develops this color, and ours develops this color. Basically, all the phosphate tests are based on the same chemical reaction. What you're doing is you're reacting phosphate with molybdic acid, and you're forming a polymer that is, which is referred to as molybdenum fluid. It's a polymolybdate compound, which is yellow. And we use a reducing agent, which turns it to a blue color. We use a slightly different approach, which we were forced to do. You'll see that one of the big differences between this is this referred to as a GBAT or a test well or whatever is referred to as. The way you look at this is you're looking at it through here. So you're looking at a lot of sample. It's deep. I mean, that's about 2 inches of sample that you're looking at. So you've got a lot of color. The deeper, the more you look through, the deeper, the more sensitive your test becomes, because the color is multiplied as the dimension of the container increases. So you're looking through deep waters. It goes dark. Now you're looking through about 1/8 of an inch at most of sample. So obviously, somebody's got an advantage here as far as sensitivity. It's a lot more sensitive here than here. So what we had to do to compensate for that, we had to come up with reagents that were much more sensitive than what is conventionally available in this way. So we've got another proprietary approach that gives us comparable sensitivity in the shallow well as you have in the deep well, which is one of the reasons why we have a yellow, green, instead of blue like everybody else. Again, though, you have to be very careful when measuring phosphate. Phosphate is a tricky, phosphate reagent, whether they're ours or somebody else's, is a very tricky reagent. A lot of people make the mistake of thinking that whatever I throw into this reagent, if it gives me a blue color, I've got phosphate. That's not the case. I mean, very often it's recommended, for example, that you test, Julian does this. Julian recommends that if you want to test a carbon for phosphate, that you throw a particle of the reagent into phosphate reagent, and if you get a stream of blue coming off from it, it means there's phosphate in the carbon. That's garbage. There's no truth to that whatsoever. It's totally false. Because for a phosphate reagent to work, the acidity of the reagent has to be perfect. The concentration of the molybdic acid has to be perfect. So the reagent concentration has to be ideal. Anything that is not perfect, you're either going to get a false positive reading or you're going to get a false negative reading. Why is that? Because the same reagent is used to measure half a dozen other things. And the way you distinguish between those other things is by adjusting the acidity and the concentration of the components. So the very same reagent is used to measure silicate. You use exactly the same reagent to measure silicate as you use to measure phosphate. The only difference is the concentration of the components. You can measure carbonates with that reagent by adjusting. Well, you've got lots of carbonates in carbon. Carbon is full of ash, which is just another word for carbonates. So everything has to be just right. if you adjust the reagent at a certain point, the reagent will measure molybdate. Well, the reagent is already full of molybdate. It's loaded with molybdic acid. And you adjust the reagent to a point, basically what you get a high blank. Basically, the reagent starts measuring the molybdate that's in the reagent itself. So you get a high blank. So depending on how the components are adjusted, you can measure lots of things with molybdic acid type reagents. So it's very important that everything be just right. It's the same, for example, if you want to measure if you have phosphate in a product. People do that. They'll take marine buffer, or they'll take somebody else's buffer or something like that, drop it inside in a reagent or make a real concentrated solution of it, test it for phosphate, and the thing turns blue. This thing's loaded with phosphate. It's not. All that is saying is that you're just screwing up the reagent. If you want to measure phosphate or something like that, basically you've got to adjust the concentrations of whatever you're measuring so that the reagent can handle it. Generally, these reagents are designed to measure salt water at the alkalinity that salt water normally has. If you've got something that will overcome the acidity of the reagent, then the reagent's not going to work properly. If it gives you false high or false low will depend on how much molybdic acid is present. And the thing is there's not just one reagent to measure phosphate. There's lots of reagents to measure phosphate because there's lots of ratios that will measure phosphate. There's lots of ratios that will measure silicate. How much acidity you need depends on how much molybdate you in the reagent. So you can, in other words, there are ways to adjust that reagent so that you need less acidity, or you can do it so you need more acidity, depending on the other components in the reagent. So that is a critical thing in making the molybdate test work. We're coming out with a silicate test, and we're using exactly the same reagent. We're using phosphate. We just adjusted it. In one case, it's adjusted to measure phosphate, in the other, it's adjusted to measure silicate.
Have you measured the level of phosphate you put in tap water?
It varies a lot. We've seen it from zero, no detectable phosphate, to as high as 2 parts per million phosphate, which is a lot. So it's quite variable. As a matter of fact, we got very comfortable because it used to be so low, and we got very comfortable for making up water for each tanks, etc., with tap water, not bottling them. And we got very lax at measuring it. And one day we discovered we were having problems measuring water was loaded with phosphate. So if you're going to use tap water to make sure you measure your phosphate, I mean, it's probably the same problem. It will vary a lot. Probably, as I said, go from 0 to 2 or 3 parts per million, which was off scale. If you're going to use it, measure it. And silicate is another test that's getting to be important. I don't think too many companies offer that. TAC offers it. The aquarium companies do not really offer it. We are coming out with it. Have a silicate test. It's ready to go. It's just waiting for package. As far as Gwinnett water is around 20 parts per million silicate, which is not bad considering that natural seawater has approximately 10 parts per million silicate. That doesn't mean you should have 10 parts per million. You probably want to have less than that. That's one of the components you probably want to have less than natural seawater. But it's not the worst component. The other biggie in the reef aquarium, in particular, to a lesser extent, marine aquarium, is calcium. Calcium is a very important test for many reasons. Corals depend on it. Everybody's hung up on it. There's a lot of dispute different opinions as to what your calcium ought to be. Some people feel that your calcium ought to be around 450 or 500, which is higher than natural seawater. My particular feeling is that it should be around natural seawater, which is about 380 to 400. And calcium test kits generally all follow the same approach. They're all titration procedures. Titration basically means that you're adding drops of something to something else, and it reacts with it. And you add these drops until the reaction stops. You count the drops, basically. How much you have, what you're measuring is based on the number of drops that you've added. The calcium, all the calcium kits that are available currently use titration. The main titrant, which is the material that is used to chelate the calcium, in other words, to take the calcium out of solution, is EDTA. A few others are used, but that it's mainly EDTA. And EDTA reacts hydroxide, which is very often supplied in a plastic bottle that breathes, is that over the storage of that kit, that bottle of potassium hydroxide is absorbing CO2 through the bottle itself. That is basically reducing the amount of hydroxide present in this forming carbonate. So what you're doing is you're actually forming carbonate. And that, in the potassium hydroxide, that can be a serious problem because it changes. Calcium carbonate is not soluble, so you start precipitating out calcium as well as magnesium, and you're not precipitating out all the magnesium because you don't have all the hydroxide that you need to dissolve. So that can be complicated. And the solution to that is simple. You have to take some steps to protect the potassium hydroxide. The other problem that you encounter is very common. I don't know how many of you follow it on Farm Reserve, but very often the question comes up. A lot of people that use aquarium systems very often get a low answer. I'm sorry. Okay, yeah. My thinking is bad. But they get a low answer or a high answer. And sometimes they get either one, but generally what happens in a test where the calcium, you get a cloudy mess, you precipitate the magnesium hydroxide, you've got a cloudy solution. What you're getting, they generally get a higher answer. What happens is the EDTA that is used to titrate also interacts with some of the precipitated magnesium. And so you need more EDTA than you actually need to run the test. Which may be why some people recommend using more potassium hydroxide, because when they do that, you're going to also co-precipitate some calcium, which is going to compensate for the high bias that you would be getting if you weren't doing it. So you've got these biases going on at the same time. Another thing to consider is the end. A lot of people want a clear endpoint when you start adding those stupid drops. Is it over yet? You know, what's the? There's two approaches to that. C-test has a reasonable approach. They've got a decent endpoint. Then you got Red Sea has a really clear endpoint. Well, the reason is because they got a precision of 50 milligrams per liter. Each drop is worth 50 milligrams. Well, anybody can get a clear endpoint with that. If you're going to go, every drop's going to be worth 50 milligrams per liter, it's easy to get a clear endpoint. If each drop is worth 20 milligrams per liter, it's a lot harder to get a clear endpoint. If each drop is worth only 10 milligrams per liter, it's even harder to get a clear endpoint. The smaller the number it gets, the harder it's going to be to get a clear endpoint. The easy way out is just to make it, do what Red Sea does.
So you're saying that the Red Sea test kit is too gross in its determination?
Well, if you're satisfied with plus or minus 50, it's fine.
Okay.
I had somebody on CompuServe ask me a question the other day, saying he was adding calcium to his tank, But as best as I could figure out, he was only adding enough to raise his calcium by 20 to 25 milligrams per liter when he was doing the addition. He said he wasn't showing up on the Red Sea test kit. Well, it wasn't showing up because he couldn't tell the difference. He wasn't making, for the Red Sea test to show a difference of 1 drop, you've got to have a difference of at least 50 milligrams. And he wasn't adding that much, so he wasn't seeing it. That's why it wasn't because the calcium he was adding wasn't showing up. It's because the test kit didn't have the resolution to show what he was adding. So I said, well, measure it before you start adding, and add it during the week. And at the end of the week, maybe you've added up to about 100 milligrams or so. Then measure it. You should be able to see. You should have a difference of at least 2 drops there from the beginning of the week to the end of the week, because you've gone up 100 milligrams. But if you go up, generally, to me, that's not enough resolution. I think that's actually probably at least 20. I'd like to see at least 20 milligrams per liter. Yeah.
Do you think you could make that more accurate by doubling all your numbers? Like if instead, on that particular kit, you use 4 milliliters of water to start, and then you do 4 drops.
Yeah,
Double
if
it
you
to
double
8,
the volume, if
and
you
then
double
double
the
the
volume of your test sample, then you're cutting, so your drops are now worth 25 instead of 50.
So you think that would be?
You can get around it that way. You can have whatever, whatever resolution you want by adjusting the volume of your sample. Make sure though that you use this proper amount of potassium hydroxide for the size of the sample. But the titrating reagents, depending on the size of the samples, you can change it yourself. You can modify your kit by either increasing or decreasing it. If you've got a kit that measures 20 milligrams per liter and you can't tell the difference, you could half your sample size and change it to 40. Each drop is going to be worth 40. You can't do that. That's something that you can do. If you have doubts about how you're reading your kits, but sometimes that's something that you can do. You can experiment with it so that you can judge whether or not you're actually reading it correctly.
Dr. Morin, I've heard a lot of things from people recently about calcium saying that their corals precipitate calcium out of the tank so fast they can't measure any calcium in the water at all. Is that legitimate at all? I've heard
Not
several
measuring
people.
any at all?
Yeah, people have said, I put it in and it's gone, instantly. People have said, no, you're not actually measuring a level. You should be measuring utilization of how much calcium you can utilize.
But not adding any calcium to the tank at all, I would not expect that your tank would ever, basically the utilization of calcium will drop off, and I would not expect that a tank, even with zero addition, that it would ever run much below.
Really?
I'd say 250 bar. Once you get to 250, your call they're just going to stop.
So you're basically saturating the utilization.
So, there's something wrong with the test, where it's just a lot of hyperbole.
Oh, there's not a lot of that.
And there's hyperbole in this hobby. Not just manufacturers. Hobbyists does it too. Okay, another test that is important is where Seachem gets to drag. Referring to the calcium, we're coming out with a calcium kit, by the way. We had our calcium kit. We stopped selling it about 3 or 4 months ago. It was done, we stopped selling it. Some people think, well, I like your kit, why did you stop selling it? I can't please everyone. The reason we stopped selling it was because we ran into a number of, our approach there was different. We did the titration with a backwards titration where basically you were adding, instead of adding reagent to sample, you were adding sample to reagent. And when we originally developed the tests and the evaluations that we did, we didn't see any magnesium interference. But subsequently, we never figured out why. Some tanks we see no magnesium interference, and other tanks we do. And basically the interfering component is magnesium. We never figured out why it does it and why it doesn't. So we changed our approach. We're now going back to titration like everybody else. But our kit is different in that when you do, we're going to package the potassium hydroxide differently so that it's more stable, and we're going to do a physical separation. Some people aren't going to like it, right up front, but we think it's the better way to approach it, that when you do the precipitation, the next step is going to be to take that sample, pour it through a column, physically remove the magnesium, so that you'll end up with a clear filtrate, and then you measure the calcium in that clear filtrate. So there's going to be there's a filtration step in it. It will be a 90 test. It will be more expensive than the old kit, which only did 20 tests, but it's going to do 90 tests. And it's going to be, how do they put in the electronics? It's cable ready, it's going to be strontium ready. Because that's another thing that's in the works, and it's pretty well near completion. And rather, people are probably going to complain that we're forcing people that want to use our strontium to buy our calcium kit. But the reason we're doing that is that the strontium kit uses all of the components that are used in the calcium kit, plus it uses leftover samples from the calcium kit. So it doesn't make sense to have somebody who wants the strontium to pay a higher price to buy everything that they've already got in the calcium kit. So basically the strontium kit is going to be an option to the calcium. So the calcium is going to come in one box and have another little box that will be the strontium option. You can't use the strontium kit without the calcium. That's basically what we're doing. The other thing that I consider important is iodide. A lot of people keep reading about supplementing your tank with iodide. How much iodide do I need? Iodide. You hear about it all the time. Of course, it's great that iodide, of course, don't like iodide. And the problem is that nobody knows what they've got into it, including us. So basically we developed an iodide test. Some of you have looked at a beta version of it, and it's almost ready for release now. This is a prototype of the packaging. It will look just like this. All our kits, by the way, will go to this format, because we used to get complaints about bottles falling out of the box, not being able to figure out how to put the bottle back in the box. So we're making it easy. The bottles all have they've all got their hole, so you just have to put the pegs in the holes, and they'll still use the test well. This basically is a real iodide kit. The label is computer simulated, but that's basically what it will look like. It will do 75 tests, like all our other tests. It has one reagent. It has 2 containers of it. Each container will do 35 tests. And then it has another reagent. And this is what we tried. People that have looked at it already can probably speak to this. But we tried to get away from doing this, and we discovered we couldn't, so we're going. What we did is you need 2 reagents, and the number 2 reagent is unstable. Tried all kinds of versions of it to make it stable, but it didn't work. No matter what you did after a couple of weeks, stuff fell apart. You couldn't use it anymore. So what we're supplying you is with a stable form of the reagent in a vial, an empty vial. This is where people are really going to get us. The batteries are not included. Your DI water, we don't include the DI water. You'll have to go to the store and get some DI water. Don't recommend RO water, because RO water probably not going to be pure enough. We need pure distilled or DI water. We're just going to fill this container with that water. We have a measuring device. We're taking a very small amount of this reagent, mixing it in this water. That is going to be your working number 2 reagent. It's going to be good for 2 hours. After 2 hours, you throw it away. And so if there's more than 2 hours between testing, then you make it up each time. That's basically the approach that we're taking with it. And we also will supply you with a reference sample, which we do with all our kits. Some people ask us, well, why don't you have an expiration date? Lots of kits are now putting expiration dates on. I don't believe in expiration dates. The main reason I don't believe in expiration dates is that I consider them phony. Most times expiration dates are artificial. You can have an expiration date and stuff can go bad way before the expiration. On the other hand, you can have something that's good 4 years after the expiration date, and you're throwing out something that's perfectly good. So what we're doing is we're putting a reference sample in all our test kits. This one happens to be natural seawater concentration iodide. So that when you can test this, and you know what it's supposed to look like, you can compare it to the color scale, and it looks something like this. It's a blue scale. And it will tell you whether or not your reagent is in. And that's true for all our kits. That's basically what we do. If you use our kits, the reference says it's not testing the way it's supposed to, we'll replace the reagents.
Is that reference stable pretty much indefinitely?
We hope so. That's the only problem we've run into with our approach of having a reference sample, and we've been learning as we go along, is that the reagents don't go bad, the reference and we end up having to replace reagent that's perfectly good because the reference was bad. And we've gone through that with all our other kits, and we've got them all down now where we're confident that they're stable, and they're proven to be stable.
But how much DI water would it take to do an entire all the tests if you how much?
Well, it depends. If you ran the whole test at one sitting, you would just need.
But I mean, if you did each one differently.
If you did each one differently, then you would need, well, you'd need 5 ml times 75. What's that? 75 times 5 ml. That's how much DI water you would use. Generally, you will probably run more than one at a time. My experience with Greek people, including myself and Jim in particular, is that they're pretty neurotic. And they're not going to be satisfied with running one test at a time. As a matter of fact, there's 6 wells here, and I'll bet you most of them will run all 6 wells on and run the reference sample also at the same time.
In fact, didn't we ask for a bigger plate?
Yeah, well, you got a little bigger.
No, plate.
Oh,
Test
plate, oh, test plate, well, this is it. It's in the box.
Just save them as you use the distance.
So,
I can see me going down there wave every week with
now
a
the
little mile
test,
and asking for
the
our
test
own
is
ones.
very, very sensitive.
DI water.
And it's going to be important that the instructions be followed to the letter. Jim kind of learned that this weekend at Magna. It kind of got sloppy, and then you have to go do it over again. But it's going to have to be done. It's very sensitive. There's another kit that's coming out by a firm from Switzerland, I believe, but all that it does is it tells you have less than natural seawater, you have about natural seawater, or you have a lot more than natural seawater. Basically, it's a qualitative test, it's not quantitative. This test is quantitative. If you've got 0.01 milligrams per liter of iodide, it will tell you you've got 0.01 milligrams. As a matter of fact, if you look at this scale, when you get to natural seawater level, which is down here at this end of the scale, it's kind of hard to read. And a lot of you that have natural seawater concentration of iodide will probably get down and say, I can't read it. And if you follow our instructions, what you'll do is you'll cut your sample in half to DI water and shoot it down to this part of the scale where it's easier to read. So basically, you'll be cutting a 0.06 down to 0.03 where it's a lot easier to read. Because once you get up to natural seawater, it actually gets difficult. Depends how you see it. A lot of people have trouble with it.
We're testing waters measures of natural against measures of natural seawater. Has there been any research on maybe able to answer this as to what the recommendations are, maybe even above natural seawater for iodide, strontium, and other critical elements?
Dana may be able to contribute to that. I can tell you that in our instructions, we're being really coy. We're telling you that anything above natural seawater should be considered it experimental,
Sure.
do it at your own risk.
Well, that's what I was wondering, I was wondering if maybe somebody was able to determine that, increase levels beyond.
I suspect that that would be the case, but maybe.
Yeah, let me make a point. There was a controversy about strontium concentrations. They said that strontium was just a substitute for calcium. And that article that was in Aquarium Frontiers, in my opinion, was very selective. I have several references at home that state quite clearly that increased strontium concentrations will increase coral growth. Now, whether or not it was strictly due to the strontium, when they tried to limit their factors, but obviously they couldn't.
Well, and obviously there are plenty of which where if you increase it too much, you may actually retard growth too. That's what I'm wondering is if there's any research done to establish those ballparks like the
Yeah.
calcium.
Yeah.
Should be at a specific level to maximize calcification, as well as pH and things like that. But what about the extra nutrients? Because we're testing now for iodide and strontium. I'm just curious if there's any targets.
Let me make a comment about iodine. Julian Sprung said that it was necessary to detoxify the oxygen that corals produce. I got that reference and that wasn't stated in there, so I'm not quite sure where he's coming from. But I think that's a very interesting idea. I would just definitely want to get on those kids and look at it.
We're excited about it because we think what it will allow people to do, what it will allow to happen, is there will be hopefully a lot of information generated where people will be keeping their tanks experimentally at higher than natural seawater level or below natural seawater level and comparing and seeing what happens. Up to now, you've had people saying this happens when I add iodide, but they don't really know what the actual concentration was.
I have a kind of marketing idea for you maybe. A lot of people with DI units don't know when they might be getting poured. A lot of times if you go to a store, you don't know how good the DI is. You might want to sell a package of deionized water that you know is deionized that will work with your test kits for people who don't really know how to get it or where to get it.
Well, I'll tell you one thing about our marketing approach. I won't do that because I can't make money selling DI water at the grocery store. A lot of people ask me, why are you so against phosphate? Why don't you sell calcium hydroxide? We don't sell calcium hydroxide. One, because I'm not very enthusiastic about it, but that's not the main reason. The other reason is that we won't sell it because I can't compete with big lime like K-Line. And I don't see any reason to sell you calcium hydroxide at a much higher price for the same thing, because there's really nothing I can do to it to change it. If I'm going to put a high price on it, there should be more done to it than put a fancy label on it. So if I can't alter it to significantly improve what it will do, there's really no reason to sell it. So just go with Kmart and buy pickling lime.
There's not
Or-
research,
or
there's not
with-
research grade with that versus, when you buy this stuff from Kmart or Walmart, it's not a lower grade than on the research.
Generally, there's no difference between the grades, even reagent grades are the same. The main difference between the reagent grades and something that you will do, is the way it's been treated from when it was produced, from when it was produced and what it was treated in between. That's like what makes the difference between food grade and agricultural grade. Food grade has to meet certain storage requirements. You can't put it next to malodor, for example. Whereas agricultural grade, you really don't care. So that's one of the basics. Another thing about reagent grade, generally very often, not in all cases, but very often the only difference is that one has an analysis and the other one doesn't. But as far as what it is, it's the same stuff. One's been tested and the other one has not. As far as reagent grade calcium hydroxide, generally when asking you, people go to reagent grade calcium oxide rather than calcium hydroxide, because calcium oxide can be produced rather than can be produced in the laboratory in very pure form, but there's no real reason for it. The impurities that are present in calcium hydroxide are probably actually beneficial. You've got basically what you've got. You've got strontium in there. You probably have approximately what you really want in the first place. And you've got other things like sodium, potassium, and they have a little bit of carbonate. basically they're innocuous things that don't matter. So why spend a lot of money to be very cost ineffective to get something that's pure or purity that you don't need?
My question on the DI water was, how do you know, or are you confident that the quality of DI water that a person would just buy at the store would not affect your test in a bad way?
If you buy DI or distilled water at a grocery store,
Oh, distilled would work too?
distilled is
Oh,
fine.
okay.
Distilled or DI water bought from a grocery store will be fine.
I didn't know distilled would work, but distilled would be pretty good. Confidence in the quality of that.
The main thing that you want to avoid, the reason I say not RO water is because it probably would be all right if enough time elapsed. It's basically something that will interfere with the test. We get chlorine, and a lot of RO units don't remove chlorine, and chlorine removers. If you have a dechlorinator that was used, and it's been there, it will interfere with the test. That's in the instructions. We say that if you have added water to your tank and have used tap water, do not test for at least wait 24 hours before testing. If you use the dechlorinator, wait 24 hours before testing, because the dechlorinator will interfere with the test, and so will chlorine.
Dr. Morin, when I reprinted your article in this month's Reefscape, one of the things that you had mentioned was that you had really very low confidence of the commercially available RO units, which is DI, and I was hung in effigy and crucified because of that.
So was I.
Would you mind taking a few minutes to explain your reasoning behind that?
My reasoning behind it is that for a given amount of money that you will spend, if you're going to spend under $100, 125 or whatever, you're going to do a lot better with a DI unit than an RO. The main reason being is that a DI unit will give you much better quality than the RO water. Plus the DI unit, even if it's aquarium farms, water, whatever, what you have in a resin, all the resins that are used in DI units have built into them an indicator dye. It tells you when the stuff is used, and you can watch it being consumed. You know when to stop using it. If you've got an economical RO unit, you don't have the foggiest idea, because they don't come with conductivity. So you could be using that thing, unless you're going to be running tests on the water that's coming off that unit, and you do it religiously. You're not, and you select the right materials to test.
Which is what? Phosphate silicate?
Well, not necessarily. Phosphates, you could, but if you don't have phosphate in the water to begin with, it's not going to tell you much of anything. Silicates are usually present. And again, it depends on the type of water you have. Generally, RO units do not, either way I've seen RO units before, they don't make that much of a difference with Atlanta water. Because Atlanta water is pretty good water. We don't know how lucky we are. We have pretty good water compared to a lot of parts of the country. If you've got really wretched water, an RO unit will look a lot more impressive, because the difference that is much more evident than if you've got water pretty strong. But my main point was that for the amount of money that you're going to spend, you're much better off with a DI unit. Now, if you're willing to spend enough money for a unit, a more sophisticated unit, one that comes with a conductivity meter on it, yeah, I know RO makes sense, but you're going to spend a lot of money on it. And actually, even if you're going to spend that kind of money, for the kind of money you're going to spend for that kind of money, you could probably get a triple column DI unit that would go from carbonate to DI units, to DI resin. You'd have the indicator there as well. And also, the other DI units will give you good quality water much faster than an RO unit. If you buy a really small RO unit, you could tie up your kitchen sink for the whole day just to make a water change. So, those are factors that you have to take into consideration. Generally, when people push an RO unit, they don't bring those factors out. If you're going to attach it permanently, it's a different story. But then you're not just gonna spend $100, $125 if you're gonna get a permanent unit. Plumb it permanently to your plumbing, it's gonna be an expensive. So really what I was talking about there were this really small units that go for about under $125. The main thing I have against them is that they give you a false sense of security. That you don't know when you're going to go bad. Matter of fact, there was some stuff on conference this last week on that where somebody had a tank crash because of the RO unit went out and you didn't know it. And that type of thing can happen easily. It won't happen with a DI. As long as you've got eyes to look at the rest of it, it's not going to happen.
So for the average hobbyist, particularly here in Atlanta with better water, like a little, you know, like the current pharmaceuticals.
Yes.
You can see it.
Here I am recommending a
Polish the
aquarium.
water.
But it
Done it again,
aquarium
Dr.
farm units will,
2 times
will
today.
work. Is a good deal in Atlanta because the quality polishes the water. But if you live in South Florida, it's probably not a good idea because it will probably last about a week and a half and then it'll be gone. But here, it's, you know, so that was my main point. I really not out to knock RO units to knock RO units. A lot of people seem to think that RO units are the way to go, and that's the only way to go. And I think you have to take cost into consideration in what the unit will do and what it will not do. And what I don't like about the economy RO units comes down to is you don't know when they're going.
I live up in Dalton, we get water straight from the carcass hills. I couldn't keep any invertebrates or even sclerophyll alive until I got already, I did get one with a conductivity meter and you have the DI, which I haven't been using yet.
Okay, well, that's the perfect, that makes sense. They have an RO unit and a DI together. That's